Welcome to This Explainer. I'm absolutely pumped to take you on a journey today that is going to completely transform how you look at something we literally walk all over every single day. We're talking about dirt, just a simple handful of soil. I know, it might look incredibly basic, maybe even boring to some, but right beneath our feet is a highly complex, completely hidden world, and it's just waiting to be decoded.
Seriously, think about it for a second. What secrets are actually hiding in a single handful of dirt? Well, in the laboratory, scientists treat a soil sample like a full-blown forensic mystery. To unlock its potential, to understand if it can grow a mighty oak tree, sustain a vital crop, or even withstand a torrential flood, that soil has to be put through a rigorous gauntlet of laboratory trials to uncover its true nature.
So, to solve this forensic mystery, we're going to follow the exact roadmap used in professional soil analysis labs. We've got 5 intense trials today: uncovering hidden moisture, measuring pH and salinity, determining lime content, decoding soil texture, and finally testing aggregate stability.
All right, let's jump right into Trial 1, Uncovering Hidden Moisture.
Our very first laboratory trial is all about stripping away variables by blasting the soil with extreme heat. You see, soil fresh from the ground, or even just sitting in a room as air-dry soil, which scientists refer to as HKT, is super deceptive. It holds invisible water weight that literally fluctuates with the weather. So step 1, we weigh it. Step 2, we throw it into an oven and bake it at 105 degrees Celsius for a full 24 hours. Then step 3, we cool it down in a perfectly moisture-free chamber called a desiccator. And step 4, we weigh it again to get our oven-dry soil weight, or FKT. This baking process reveals the exact moisture percentage, but more importantly, it ensures that every single test we run after this has a perfectly dry, mathematically pure baseline.
Once we've got those strict baselines, we move on to what I like to call the drowning phase. We're making a saturation paste. We take our soil and slowly mix it with distilled water until it reaches its absolute breaking point. And how do we know it's there? The criteria are surprisingly strict. The surface has to glisten and shine. There can be absolutely zero dry lumps left. And when you scoop it, the paste has to slide completely and cleanly right off a spatula without sticking. Then we seal up this perfect mud and let it rest overnight. We're essentially waking the soil up, getting it ready for the electrical and chemical probing that's coming next.
Moving right along, we hit Trial 2, Measuring pH and Salinity.
Okay, so our mud has rested overnight, and now we're going to stick digital probes right into it to figure out its chemical temperament. We're talking about mapping the soil on a scale that goes from very strong acid on the low end all the way up to very strong alkali on the high end. And why does this actually matter? Well, pH is absolutely crucial because it dictates whether plants can actually eat the nutrients in the ground. If the soil is too acidic or too alkaline, those nutrients become chemically locked away. A plant could literally be sitting in a total buffet of fertilizer and still starve to death just because the pH is wrong. Right after checking the pH, we hunt for salt. Our digital probe measures electrical conductivity, or EC, in decisiemens per meter. This probe basically acts as a lie detector for hidden salts. When that EC number spikes above 15, we are officially in the very salty danger zone. This is a massive red flag warning us that planting crops here could be a total disaster. Excessive salt acts like a sponge. It pulls water away from plant roots and literally dehydrates the crops from the inside out. No way we want that.
Okay, up next is Trial 3, Determining Lime Content.
Having mapped out the chemical vibes, we advance to what is, hands down, the most explosive trial: determining the lime content using a specialized piece of glassware called a Scheibler calcimeter. Lime, which is calcium carbonate, deeply affects how soil is structured. To find out exactly how much is hiding in our sample, we run an acid test. We carefully drop just half a gram to 1 gram of soil into a bottle. Then, we introduce 10 to 15 milliliters of a 10% hydrochloric acid solution. We seal the system tight and give it a shake. Instantly, a dramatic chemical reaction goes off. The acid aggressively attacks the lime, dissolving it and releasing carbon dioxide gas. We keep shaking until the bubbling stops, and the calcimeter captures that escaping CO2 gas so we can measure its exact volume.
Now, what's truly mind-blowing here is the sheer level of precision required. Scientists can't just trust the raw volume of gas they caught in the tube. Why? Because the actual air pressure in the laboratory changes every single day. They actually have to cross-reference their reading with a highly specific barometric pressure table just to account for the atmosphere pressing down on their experiment. It's wild.
And they literally don't stop there.
Alongside using the famous Boyle-Marriott formula to convert the gas volume to standard conditions, they also bring in a second table to correct for water vapor pressure based on the current room temperature. This double correction guarantees flawless precision, giving us the exact percentage of lime without a random weather front throwing off our math.
All right, trial 4, decoding soil texture.
For this fourth trial, we leave the pure chemistry behind and get intensely physical. We want to find the literal physical skeleton of the dirt, the sand, the silt, and the clay. To find this skeleton, the soil has to be entirely broken down into individual microscopic particles. First, it faces chemical stripping. We wash away all the salt, all the gypsum, we chemically burn off the organic matter, and dissolve the lime. What's left goes straight into a heavy-duty mixer. We add chemical dispersants and violently blend it at up to 1,800 revolutions per minute for up to 15 minutes. The whole goal here is to brutally break apart every single clump until the particles are completely isolated.
Next up is this incredibly suspenseful waiting game. This entirely dissolved mixture is poured into a massive glass cylinder filled with water. We plunge an instrument called a Bouillakos hydrometer into it, which measures the density of the floating liquid. At exactly 0 seconds, the settling begins. Because sand is heavy, it sinks to the bottom almost instantly. At precisely 40 seconds, we take a hydrometer reading to measure the silt and clay that are still floating. And then, we wait. We wait 2 full hours. By then, the silt has finally sunk, and a final reading tells us exactly how much microscopic, ultralight clay is still suspended in the water.
All of that waiting finally gives us a verdict using a brilliantly simple concept, the texture triangle. Once we've calculated our percentages of sand, silt, and clay from those hydrometer readings, we map them out. By drawing lines from the percentage of clay on the left, silt on the right, and sand on the bottom, we find the exact point where they all intersect. That intersection hands the soil its official scientific name, whether it's a sandy loam, a silty clay, or just pure, unadulterated clay.
Finally, we arrive at trial 5, testing aggregate stability.
So we know exactly what our soil is made of now. But the real question is, how tough is it? This final trial is basically an earthquake and a flood simulation mashed together. We take structurally intact soil clumps, called aggregates, and subject them to a super aggressive mechanical test known as wet sieving. We place just 4 grams of the dry soil on a fine sieve with a 0.25 millimeter mesh. Then we fully submerge it in pure water and mechanically shake it vertically 34 times a minute for 3 solid minutes. Why go to all this trouble? Because it perfectly mimics real-world environmental stress. It tells us if this soil is going to hold together and keep its structure during a massive rainstorm, or if it's just going to instantly dissolve and wash away in a catastrophic mudslide. Now, any soil chunks that are actually tough enough to survive that aggressive mechanical shaking, they are then subjected to absolute chemical torture to figure out what is holding them together. Based on our earlier pH test, alkaline soils get treated with a dispersive chemical called sodium hexametaphosphate, while acidic soils are attacked with sodium hydroxide. We just keep sieving them in these harsh chemicals until absolutely nothing is left but indestructible, pure sand grains and incredibly stubborn plant roots.
By measuring what washed away during the water test versus what only surrendered to the chemical test, we can calculate the soil's true structural strength. Just like the source material puts it, the entire goal here is to determine the resistance of soil aggregates against breakdown. Seeing a sample survive these intense physical shakings and chemical washings proves just how remarkably resilient the earth beneath us really is.
From baking ovens and acid explosions to violent blending and chemical shakedowns, a single handful of dirt contains a meticulously balanced, completely hidden world. Thank you so much for hanging out with me on this explainer today. I want to leave you with this final thought. After seeing the incredibly complex recipe of sand, silt, clay, lime, and minerals all working together to basically hold up our entire world, how are you going to look at the ground differently the next time you step outside after it rains? Keep exploring, and I'll catch you in the next one.